Okay, let me enlarge the slides. Okay, in the last lesson, we started examining the so-called Sommerfeld half-space problem, which in addition to being a classical configuration in applied electromagnetics, has been used in this course to illustrate some important examples of wave species. In particular, we saw that by exciting such a configuration with, for instance, a vertical electric dipole, one could, just a moment. Okay. Good morning also to Clementina. One could, for example, derive by means of the steepest descent method the contribution of the saddle point without to be actually the geometrical optics contribution to the field. We examined in particular the reflected field yesterday, the other lesson. And in addition to that, we also considered singularities of the spectral integrand. And we found that, for instance, there were poles, the so-called Sommerfeld poles, to which kind of surface waves were associated. And depending on the specific media involved, those surface waves could be either named Zenek waves. That would be the case, for example, of soil at radio frequencies, or at higher frequencies, say optical frequencies, in the case of an air-metal interface, the surface wave would be instead called a surface plasmon polariton wave. But in both cases, the analytical origin of this kind of wave is the same. That's related to a pole singularity. And today we will see some further examples, important examples of waves associated with pole singularities. But in addition to that, we also mentioned briefly the existence of lateral waves, that is waves associated with branch cut integrals that arise when you deform the integration contour beyond certain angles. Now, we will start the lesson today addressing these lateral waves in order to provide some more information and also physical insight into this kind of wave species. And to start with, let us consider the basic problem of plane wave reflection and refraction at a planar interface between two semi-infinite media. As usual, we will consider very simple media, so homogeneous lossless isotropic dielectrics. When a plane wave impinges on a planar interface between two such media, what happens, as you know very well, is that there arises a reflected wave in the medium from which the incident wave impinges, and there is also a transmitted wave in the other medium. Now, the direction of the reflected wave is such that the reflection angle is always equal to the incident angle, whereas the transmitted wave is generally refracted in the second medium at a different transmission angle. And in particular, if the wave impinges from the optically denser medium, that is, from the medium with a higher dielectric constant, that is, the medium with the lower wave speed, now the refracted wave will emerge at a transmission angle that is larger than the incident angle, as you can see here in this figure. So what happens is that if you now increase the incident angle, you will arrive at a critical angle for which the transmitted ray will be emitted at a grazing direction. That is, the transmitted angle will be equal to pi over 2. In this figure, the transmitted angle has been indicated in a wrong manner. That should be measured from the normal to the interface rather than from the interface itself. So that's a typo. If you still increase the incident angle beyond the critical angle, then total refraction occurs, which means that the entire real power associated with the incident wave is reflected back, so there is no average transfer of power in the second medium. However, in the second medium, a wave does exist, but that's a different kind of wave with respect to the incident wave, since it is an evanescent wave. There is a wave that propagates grazing to the interface, while it attenuates in a direction orthogonal to the interface. This kind of wave, by the way, since we are dealing with complex analysis and complex numbers, can be described in terms of the usual formulas involving the transmitted angle theta t. However, you should extend the value of theta t to complex numbers, in particular to a complex number whose real part is equal to pi over 2 and whose imaginary parts depends on the incident angle and on the property of the involved media. Okay, this is very well known, of course. And as you know, plane waves are the basis of geometrical optics. So usually this process of reflection and refraction can be interpreted in ray optical terms. So you will speak of wavefronts, rays, ray tubes, that is bundles of rays which transport energy in space. However, consider the situation when the incident angle is less than the critical angle, and consider a ray tube. So here you can see highlighted in cyan the ray tube associated with the incident wave, which transports some power. This gives rise to a reflected ray tube, so part of that power is reflected back, and the remaining portion is refracted in the narrower ray tube that is transmitted in the upper medium. Now, the same kind of things occurs beyond the critical angle. So if you now consider a larger incident angle, larger than the critical angle, then in this case, the real power is only associated with the incident and the reflected waves. So you have a complete transfer of real power, because in the upper medium, only a reactive kind of power is present. So there is energy in the vicinity of the interface, but no net transport of power above. Now, the point is that exactly at the critical angle, something quite strange occurs, because exactly at the critical angle, since the transmitted angle is equal to pi over 2, the transmitted ray tube shrinks to a zero cross-section. So actually, there is no space for power to go, which is quite strange because power must be conserved. So that power must go somewhere. So this is one of those situations in which geometrical optics fails, because it does not ensure a basic property like conservation of energy. Now, it is plausible, however, that the critically refracted ray, that is the evanescent wave that propagates grazing to the interface, may in some way react back in the denser medium, so to produce some kind of wave that is the so-called lateral wave. And this is the mechanism that is illustrated in the bottom figure, where consider the incident ray that emanates from some kind of source which is present in the lower medium. Now, this emitted ray at the critical angle produces the refracted wave, that is the evanescent wave that propagates horizontally. But during this propagation, there will be some power that comes back in the denser medium, and it will do that exactly at the same critical angle as before. So this defines a region, the domain of existence of this lateral wave, that depends on the position of the source and on the critical angle. As line is the left boundary of this domain of existence. And so this could be a plausible mechanism for power to be conserved, in at least in ray terms. We will see that this is actually the case, and to find a rigorous foundation for this kind of prediction, let us come back to our analytical representation of the fields in terms of spectral integrals. So let us come back to the situation we illustrated in the previous lesson, in which again we have a source like a vertical electric dipole, and we have expressed for example, the reflected field in terms of an integral that is performed along the entire real axis of the complex k-ρ plane. I remind you that k-ρ is the radial wave number. We have expressed the potential, any potential, in terms of inverse Hankel transforms, so in terms of integrals that are performed in this complex plane. And originally, the integration path would run on the positive real axis. However, we managed to extend the integration contour. So this is now the orange one. And the situation in terms of singularities of the integrand is the one represented here. So we have branch points that are associated with the medium K1. That I remind you that in our previous lesson, the source was in a vacuum. So K1 could be the vacuum wave number. And for this reason, K1 is here represented as a real number. Whereas the upper medium was a dielectric, possibly lossy. So in this case, K2, the other pair of branch points, are located in the fourth and second quadrants of the complex plane. The relevant branch cuts, as usual, are the Sommerfeld branch cuts, so they are hyperbolic. You can see the shape of the hyperbolas in connection with K2 and minus K2. But those hyperbolas degenerate into segments or half lines that lie along the real or imaginary axis of the complex plane when the wave number of the medium becomes real, as in the case of K1. Furthermore, we have a pole singularity at the Sommerfeld pole. And here you can see the steepest descent paths that correspond to observation points at the interface. So when the observation angle is pi/2, in this case, the steepest descent path that is used for the asymptotic evaluation is SDP1. However, the Cauchy theorem requires that we also detour around K2, and this produces an additional steepest descent path, number 2 in green here, which gives, however, typically a negligible contribution with respect to SDP1. That is because K2 lies somewhere in the fourth quadrant. So basically, the contribution due to the green path is negligible because it is of the order of an exponential, in which there is an imaginary part of the wave number, so there is an attenuation. So this contribution is exponentially small with respect to SDP1. We said in the previous lesson that this latter negligible contribution is the so-called lateral wave. However, if the source is in a vacuum, this contribution is negligibly small, so it can be safely neglected. But if you now remove losses in both media, and if you place the source inside the denser medium, the situation may change. And this is what we will consider next. So here is the situation that we will address. The same interface, however, now the vertical electric dipole source is in the denser medium, so it is inside the dielectric, which is assumed to be lossless, so its relative permittivity epsilon r is a real number, whereas in the upper medium now is a vacuum. All the other things remain the same as in the previous lesson. Just a moment. Okay. Here we have good morning also to Umair. Again, we have a vertical dipole that is represented in terms of an impressed electric current that is proportional to Dirac deltas. Its amplitude is this complex number here, P sub 0. Okay, we can exploit directly the formulas that we derived in the previous lesson. In particular, our starting point will be the so-called axial transmission representation of the total potential that expresses the potential in the upper and lower regions in terms of inverse Hankel transforms of order 0. Consider, for example, the lower medium here. That is, here the potential is the sum of a closed form term, which is the incident potential, a spherical wave, that the spherical wave that would exist if the source were radiating in an unbounded medium, the electric medium in this case. As you can see, there is K2 in the exponent. And then there is the reflected wave, which is not available in a closed form, but it is represented as a zero-order inverse Hankel transform. So you can see the kernel of the transform, that is the Bessel function of order 0. Then there is the one-dimensional Green's function in the lower medium. And finally, there is the current reflection coefficient minus gamma for TM polarization. In the upper medium, we have only the transmitted wave, which is also represented in terms of an inverse Hankel transform of order 0. And now, in this case, gamma, since it is the reflection coefficient for vertically polarized waves, must be written considering that the incidence now is from the dielectric, so the expression is different with respect to the previous one, and since we are switching the two media. So this is the expression that we must now consider for gamma, okay? Now, in this case, we are assuming lossless media, so both branch points are real. Here in this figure, I have displaced the little bit K2 in order for clarity, but consider that K2 is also lying on the real axis, exactly as K1. Okay. As concerns the Sommerfeld pole, well, the expression of this Sommerfeld pole is available in a closed form. It is repeated here. And since we are dealing with lossless media, now this pole will become a real pole. So we have a real wave number. And that pole will lie exactly on the branch cut associated with the wave number K1, relevant to free space. However, it will lie on the lower rim of that branch cut. So the Zernike wave that is associated with this pole is now an improper surface wave. It does not lie anymore on the top Riemann sheet, that is also called the proper Riemann sheet, the one that corresponds to waves that attenuate exponentially at infinity. So we can simply neglect this Zernike's improper surface wave in the following analysis, since the pole is not captured in any of the integral path deformations that we will be doing in the following. Now consider this representation, which is a non-spectral representation, and consider the asymptotic evaluation of the integral that we performed in the previous lesson by using the steepest descent path. We found that there is a saddle point that is located on the real axis, somewhere between the origin and the K1 wave number, and precisely this is indicated here in purple. The wave number of the saddle point is equal to K2 times the sine of theta, where note that now K2 is the larger of the two wave numbers. So that's the wave number inside the dielectric where the source resides. If we consider observation angles smaller than the critical angle, this saddle point wave number will be less than K2 times the sine of the critical angle, which by definition gives you K1. So the saddle point will be located on the left of K1. Okay, as in this figure, this is the shape of the steepest descent path that is represented in gray. The critical angle, of course, as you know, is the inverse sine of the reciprocal of the relative permittivity of the dielectric, by the way. So if you deform from the extended Sommerfeld integration path in orange to the steepest descent path in gray, which lies almost entirely on the top proper Riemann sheet. However, part of this path goes downstairs in some lower Riemann sheets in this dashed part, okay? What you obtain is that you do not capture any pole singularity, so Cauchy theorem allows you to say that the original integral is exactly equal to the integral along the steepest descent path. Okay, and now you would perform usual asymptotic evaluation to find the dominant asymptotic contribution associated with the saddle point. However, if you consider observation angles larger than the critical angle, now this means that the saddle point, which is again k2 times sine theta, is larger than k2 times sine theta critical. So this is larger than k1. And in fact, as you can see now, this saddle point is on the right of k1, but always on the left of k2. So in this case, the steepest descent path is narrower, has this shape here. And since you need to deform from the extended steepest descent path to this new steepest descent path associated with branch cut number 2, what happens is that in the deformation process, you would run into the singularity that is represented by the branch point at K1. So you must detour around that singularity, and the most convenient way to detour is to follow the steepest descent path, which is vertical and folded onto itself in green here, that is associated with the K1 branch point. So all in all, the original integral along the extended Sommerfeld integration path is the sum of two contributions. That is the contribution from the steepest descent path that goes through the saddle point, the SDP number 2. But in addition, we have also a contribution from the SDP1, and that is by definition our lateral wave. Okay. This lateral contribution is the one that we now wish to examine more closely from an analytic point of view. And to do that, let us write explicitly the lateral wave potential, which is written as an integral along the steepest descent path number 1. So again, this folded path. So you have an upper leg, the leg that goes in the vertical positive direction, that runs in some lower Riemann sheet. Then it crosses the branch cut infinitesimally on the left of K1, and then it goes down onto remaining on the top Riemann sheet, and that's the continuous green line. Okay. The integrand is the usual one, with the only difference that since we started from the extended Sommerfeld integration path, here you see the Hankel function instead of the Bessel function. And here you see 1 over 4 pi instead of 1 over 2 pi. That's the only difference. Now, we can parameterize the steepest descent path, which is vertical, by letting k rho equal to k1 minus js. That is because we are running along the vertical half line, which goes through the branch point k1. So if you let s go from 0 to infinity, you would describe the entire steepest descent path. If you wish to integrate only once from 0 to infinity, what you can do is to fold the integrand. That is, you integrate the difference of the integrand. That is, you calculate the integrand on the top sheet, and then you subtract the integrand on the bottom sheet. You need to subtract because the direction of integration is opposite on the two legs. Okay. This kind of folding of the integrand needs to be performed, however, only on the reflection coefficient gamma, because that is the only place of the integrand where square root occur. So where the evaluation is different if it is performed on the proper sheet or on some improper sheet. All the rest of the integrand is for all the rest of the integrand, this kind of thing is immaterial. So you can simply evaluate it by letting k rho be equal to k1 minus js. Finally, you have to change your integration variable. So the Jacobian in this case is given by the constant minus j. Now, explicitly, with this notation that we introduced in the previous lesson, the double square bracket, we mean the difference of something, of some function on the two parts of a folded integration path. In this case, that's explicitly minus gamma evaluated on the right part, so the top or proper part of the integration contour. That is the downward leg of the steepest descent path number 1, where both KZ1 is proper, That is because we are on the top sheet with respect to KZ1. However, we are improper with respect to K2. That is because, as you can see, this green continuous line crosses the branch cut associated with K2. So it goes downstairs with respect to K2. So we are improper with respect to K2, but proper with respect to K1. Whereas the upper leg is improper with respect to both. So we have KZ1 improper, but also KZ2 improper. Okay. So we need now to explicitly evaluate this difference by considering the explicit expression of the reflection coefficient. Let us do that. Minus gamma is minus the ratio between this numerator and this denominator, where you can see there are the vertical wave numbers, kz1 and kz2, which are in turn expressed by square roots. So every time you have a square root, you have to take a decision. Which kind of determination must I choose? And you have to do that consistently with your needs. So in this case, in order to make things simpler, it is convenient to avoid having square roots in the denominator. So we multiply numerator and denominator by the denominator with the minus sign instead of a plus sign. So this produces the difference of two squares in the denominator. And since we have squares, those squares effectively remove the square roots. Okay, so now the denominator becomes something whose value does not depend on any choice of determination of square roots. This is not the case in the numerator, where if you perform the algebra, you will find that there are some squares as well, so they are okay, they don't need to be considered. However, there are also the wave numbers kz1 and kz2 by themselves. So if you split now this new ratio as the sum of these two terms, the black term contains only squares, so this kind of function is without branch points. Okay, so it's regular at kz1. Whereas the grid part is the one that needs to be evaluated differently on the two parts. So we can say that the difference, the folded integrand, in particular the folded reflection coefficient, the value of this difference may only come from the green part, since the black part is the same on the two legs, so it cancels when you perform the difference. Now, since KZ2 is not involved in the two legs because it is anyway improper, you can take outside of this folding operator everything. So the only thing that remains inside is just the KZ1 wave number. That's the only thing that is different on the two legs of the integration path. So now we can write explicitly those two wave numbers. KZ1 by the separation relation is the square root of K1 squared minus K rho squared. But since we are moving on the steepest descent path, instead of K rho, we now write K1 minus JS. So as you can see, K1 cancels inside the square root function, and what remains is 2js plus s squared. If you do the same steps with KZ2, you will discover that there is no cancellation of the wave numbers inside the square root, so there is an additional term that is K2 squared minus K1 squared. This tells us that in the limit when s is a small number, KZ1 will tend to 0, whereas KZ2 will not. It will tend to some finite number. Why are we interested in small values of s? Well, because by Watson's lemma, the behavior for small values of s will determine, that is the local behavior of the integrand in the neighborhood of the branch point, will determine the asymptotic value of the integral. So in this limit, we may approximate KZ1 by neglecting s squared with respect to the other term, which is linear in s inside the square root. So we can let KZ1 be approximately equal to the square root of 2j K1s. So 2k1 to 1/2 times s to 1/2 times minus 1 minus j if we decide to be proper, or 1 plus j if we decide to be improper. That depends on our needs. That is because we are now taking the square root of 2j. The square root of 2j is exactly what you can see here. -1 minus j, or 1 plus j. Whereas kz2, in the limit when s tends to 0, is just this constant, the square root of k2 squared minus k1 squared. Okay, if we replace those wave numbers inside the expression of the folded reflection coefficient, what you get is this thing here reported at the bottom. And now this thing can be written more compactly as some constant gamma 0, whose expression is reported here, times s to 1/2. Now this is the information we need. This s to 1/2 is the thing that you will find inside your integral, because you can take outside everything else, because it does not depend on s. So what you need to integrate is actually s to 1/2. This comes from the gamma tm term. And then finally you have the Laplace exponential e2 minus s rho. So this kind of thing defines, by the definition of gamma functions, the ratio between the gamma function with the argument 3/2 and rho to the same exponent, 3/2. This power of rho can be joined with this square root of rho in the denominator of this term outside of the integral to produce an overall 1 over rho squared behavior. So what you can see in the box is the final asymptotic evaluation of the lateral wave. That is a constant that involves the relative permittivity of the dielectric. Then there is an exponential in which you have a purely imaginary exponent, so we have a phase term. And finally, there is the amplitude term that gives you the spreading of the lateral wave as 1 over rho squared in absolute value. Okay, this is the expression that we now need. Let us start with the phase term. The phase in the exponential term is rewritten here. It's given by k1 rho plus the square root of k2 squared minus k1 squared times the absolute value of z plus z prime. Z prime is the location of the source and z is the observation abscissa. Now this can be rewritten by multiplying and dividing the latter addend by the same square root. So you would find a ratio between k2 squared minus k1 squared and its square root. Why doing that? Well, because now we can split this ratio, and so to obtain two terms. In the first term, in red here, we have factored out k1, so the wave number of vacuum, and what remains is rho minus k1 divided by the square root of the difference of the squares of the wave numbers times the absolute value of z plus z1, z prime. In blue, you can see the other term, which is k2 times k2 divided by the square root, and again, the absolute value of z plus z prime. The reason of this splitting is that now we can give an interpretation, a geometrical interpretation of these terms. In particular, if we remind the definition of the critical angle, which is related to whose sign is related to the ratio of the wave numbers. In particular, k1 is given by k2 times the sine of the critical angle, theta c. We see that the ratio occurring in the red part is the tangent of the critical angle, whereas the ratio that occurs in the blue part is the inverse or the reciprocal of the cosine of the critical angle. So having related those ratios to quantities, to trigonometric functions of the critical angle, we may now provide a physical interpretation of this phase term, because collecting things together, you can see that now the phase term is given by k1 times this red part plus k2 times this blue part. Now, if you consider the geometry of the configuration in which you have a source at Z prime and an observation point at Z, you can see that the red part that multiplies, the red term that multiplies K1 is exactly the length of this red arrow in this figure. Now, this horizontal arrow is defined by the critical rays emitted by the source that propagates at the critical angle with respect to the vertical direction, and this impinges somewhere at the interface in this point where the red arrow starts, whereas the red arrow ends exactly at the point where the ray, if emitted at the critical angle, would react back in the denser medium to reach the observation point. This is just simple trigonometric considerations on this configuration. Whereas if you consider the blue term, that blue term will give you the sum of the lengths of the blue arrows. That is L1 associated with the emitted ray, and L3, which is the ray that is reacting back to reach the observer. So all in all, what you get is K1 L2 plus K1 times L1 plus L3. And this is exactly the phase that accumulates in a geometrical optic representation of propagation if you consider that propagation occurs in sequence through rays that propagate along this path. So this is exactly the kind of mechanism that we were mentioning at the beginning. So there is a ray emitted by the source at a critical angle that propagates for some distance along the interface and finally is reacted back, so it's reflected in a sense back in order to reach the observer. Okay. However, we have now substantiated that prediction by means of asymptotic analysis. Okay. So the phase term gives us a validation of the intuition, of the initial intuition. It is also instructive to observe that inside the domain of existence of the lateral wave, which depends on the location of the source, of course. So if the source is very close to the origin, as in this picture, in which the source is right at the origin, then the domain of existence of the lateral wave would be the region whose left boundary is defined by the critical ray that goes down, okay? Now, inside this domain of existence, the wavefronts are linear, at least in this cross-section. So that's the lateral wave that propagates with a real phase vector, beta, that is given by k2 times a unit vector, whose component, of course, along the raw direction is given by k2 times the sine of the critical angle. So it propagates along the raw direction exactly with a wave number equal to the upper wave number. So this means that there is phase matching with the wavefronts of the spherical wave, that is the wave that is directly emitted by the source in the upper medium, as you can see in this figure. But in addition to that, you can also see what happens at the left boundary, that is this oblique line. Here we are parallel to the phase vector of the lateral wave, so the wave number is equal to k2. That is exactly the wave number inside the dielectric. So again, there is phase matching. Now the phase matching is with the spherical wave that is produced by the source directly into the denser dielectric medium. So all in all, we have that there is always phase matching at all the interfaces. Okay. Let us now consider the amplitude term. As we observed, the amplitude of decay of the lateral wave is of the kind 1 over rho squared. And this is larger, that is, the decay is faster than that of the direct spherical wave. So this means that this lateral wave is generally a weak effect. Okay, that's weaker than the direct and reflected geometrical optics fields. Now, for observation points at the interface, actually, the direct and reflected geometrical optic fields tend to cancel for large radial distances. So if you have a source that is close to the air-soil interface and you are observing radio waves very far from the source, there would be a cancellation between the dominant direct and reflected geometrical optic fields. What remains, however, is that the steepest descent path integral would give you a dominant asymptotics that goes like 1 over rho to 3 over 2, which is still dominant over the lateral wave, because the lateral wave goes down as 1 over rho squared. In order to observe directly the lateral wave, so to have dominance of the lateral wave, you need to consider situations in which the medium is non-homogeneous. So consider, for example, a stratified medium in which the profile of epsilon as a function of z is as in the left figure. So you have a constant value, epsilon 1, and then starting from some abscissa z0, so beyond that abscissa, you have a growing shape of the function epsilon of z. Now, in this case, if you have a source in above z0, like here is represented on the right, and you consider the propagation of rays, since the medium is non-homogeneous, as we know, rays do not propagate along straight lines, but they produce they follow some curved path. And if the situation can be like in this figure, so if you consider all the possible rays emitted by the source, their shapes would form a caustic, so there will be a shadow region which is never reached by any of the rays that are emitted by the source. However, in this shadow region, it is possible that the lateral wave may enter. That is because the lateral wave propagates partly in the upper medium, but also at grazing angles, so medium. So by means of this mechanism of propagation, the lateral wave may penetrate the shadow region. And so when you have a situation like this, if you follow the path 2, 3 here in this figure, if your observation point is in the shadow region, the lateral wave will be the dominant asymptotic contribution to the field. And in that case, it can be observed. Okay. This is, of course, the situation when we are considering time harmonic waves. But if you consider things in the time domain, so for transient sources and fields, the situation may completely be different. And in that case, the lateral wave is very easily observed. That is, the basic reason for that is generally, when you consider transient conditions, you can distinguish the different wave constituents because at the observation point, they arrive at different times, since each wave has a different velocity. Okay, so you can record the transient waveform, and then from the study of the waveform, you can recognize the arrival of different wave species. In particular, consider again a source very close to the interface. On the left, you can see the shape of the wavefront that is propagating in the lower medium, number 1, with some velocity c1. Of course, the shape of the wavefront is spherical, so you have a sphere of radius c1 times t. So as time goes by, the radius of this sphere increases, and that's one kind of wavefront. In addition, we have, however, the lateral wavefront that, as we observed before, is made of lines. So you can imagine to rotate this configuration around the z-axis. So they are actually portion of cones. So we have conical wavefronts for the lateral wave. As concerns the upper medium, we again have spherical wavefronts. However, the radius is now c2 times t, so it's different, and it's larger since the wave is faster in the upper medium. So now, to connect everything, so the larger sphere in the upper medium and the smaller sphere in the lower medium, you can see the conical wavefronts of the lateral wave that needs to exist to have continuity of the wavefronts. Now, it may happen that in some regions of space, like in the shadow, the hatched line regions here, the lateral wave is actually the first wave that arrives at the observer. And for this reason, especially in the literature of seismology, that is called the head wave. That is because the head of the entire wave process. Okay. In the previous editions of this course, we would devote the last 2 lessons to the study of transients. This year I have changed a little bit the course, so I will not cover transient phenomena, but rather we will cover some diffraction in the time harmonic regime in the last week. However, if you are interested in transients, I will make you available the slides, so you can see also explicitly the lateral wave in the time domain. Okay, I think we can stop here. So let's come back in a 15 minutes, 5 minutes after 11, to talk about surface waves and in particular leaky waves. So see you later. Okay, let us start over. The second part of this lesson, I will talk you about surface and leaky waves. We have already seen examples of the former. As concerns surface waves, by definition, those are wave constituents that rise in a spectral representation of the field. So I'm referring now to the representation that in the previous lesson we also called it the radial transmission representation, that is obtained by deforming the original integration path in order to run along the branch cuts associated with the branch points K1 and K2 that is situated in the space problem. In a general stratified medium, and now here we generalize our configuration to the case that is depicted here, that is a structure in which we have a number of layers. For simplicity, we will consider simple media, that is homogeneous isotropic media, with wave numbers K1, K2, up to Kn. And of these layers, a number of them will have a finite thickness, but two of them, the one with wave numbers K1 and Kn, will be semi-infinite. So we have a half space above filled with medium K1 and a half space below the structure filled with medium Kn. Now it turns out that if you study the relevant spectral Green's function, the branch points are only associated with the wave numbers corresponding to the semi-infinite media. That is because the wave numbers of the intermediate finite thickness media do not give rise to multi-valued determinations of the Green's function, even if the vertical wave numbers in all media are expressed by square roots. So their value depends on the determination of the square root. However, for the intermediate layers, those square roots occur as arguments of even functions. Say, imagine cosine function. So the actual determination of the square root does not matter because an even function does not change its value if you change the sign of its argument. So for this reason, there will not occur branch points corresponding to K2, K3, and so on. So in this picture here, you can see branch points at K1, the upper medium, and Kn, the lower medium. If those are lossless, they will be located on the real axis. And in the figure, Kn is slightly displaced from the real axis, just for clarity. Of course, if the upper medium is the same as the lower medium, you will only have a pair of branch points. Okay. The point is that surface waves are associated, however, to pole singularities. So the Zernike wave is probably the simplest examples of surface wave. In that case, since, however, the electric medium was lossy, the wave number of the Zernike wave was complex. The Sommerfeld pole was located in the fourth quadrant of the complex plane. Whereas, in general, if your structure is lossless, the pole associated with surface waves will be real because there is no loss mechanism, and therefore it will be located somewhere on the real axis above the larger wave numbers of the wave numbers involved, so that the wave is a slow wave that attenuates exponentially in the semi-infinite media. This is the shape of the model field that, as I was saying, is attenuating exponentially by going at infinity in the positive direction, but also in the negative direction. The wave propagates with cylindrical wavefronts that emanate from the source, and it goes outwards. And while it propagates, however, it also attenuates in absolute value, but the attenuation is not due to any loss in the media nor to any radiation, but it's simply a geometrical attenuation due to the fact that we are dealing with cylindrical waves. So the wave spreads its power across larger and larger wavefronts, so the amplitude must decay in order to obtain conservation of power, and the decays is the typical decay of cylindrical waves like rho to 1/2. Okay, so you can see here the explicit expression of the pole contribution, which is the Hankel function evaluated at the pole wave number, here indicated as k rho surface wave. That is, again, it's a real number larger than any wave number of the semi-infinite media, times an exponential function that is e2 minus j kz1 surface wave z in the upper medium, and e2 plus j z n surface wave z in the lower medium. By exploiting the asymptotic form of the Hankel functions, valid when the absolute value of the argument is large, we can write this explicitly in terms of simple exponential functions. So also the dependence on rho contains an exponential e2 minus j k rho surface wave times rho, and then there is the spreading factor that I was mentioning before. Of course, all the wave numbers, as I was saying in the previous slide, can be calculated through square roots by exploiting the separability condition in all media. Okay. This generalizes what we discussed the last time in connection with Zenek or surface plasmon polariton waves to the situation of a general multilayer. However, from an analytic point of view, there is no difference. So the point is that surface waves are the contribution of pole singularities, and those poles in lossless media will be located on the real axis. So the wave is bound to the upper and lower interfaces. It propagates along the interfaces by transporting power in the direction, in some direction, or in general in all directions along the interface planes. If there is a perfectly conducting ground plane or any structure that is not penetrable by radiation, you will not have any electromagnetic field, for example, in one of the two half spaces, in this picture in the bottom half space. So you need just to introduce a pair of branch points associated with the upper medium, K1. But all the rest is exactly the same. This is the situation that is typically found in microwave integrated circuits, in which we have a metal ground plane and some upper medium, typically air or vacuum. If you have just a single layer of dielectric, you have the typical substrate for a microstrip line, for example. But in general, you may also accommodate a general stratification involving more than one medium. Now, remaining with in the discussion to sticking to pole singularities, it happens that when the integration path is deformed, so we now change from the spectral representation to some different representation, like the steepest descent path representation, then it is possible that in a stratified medium, so not in the Sommerfeld half space configuration, but in this more general stratified configuration, there are further complex poles that are typically located on some improper Riemann sheet. And if you cross those poles when deforming the integration path, you must take into account the contribution that arises because of the residue theorem. So you have an additional wave species that is called a leaky wave, for reasons that will be clear in a moment. For example, in this situation here, you can see there is a pair of surface wave poles located on the real axis, on the right and on the left of the branch points. So those are slow waves, because the wave number is larger than the wave number in the upper medium. But there is also a pair of pole singularities in the fourth and second quadrant, somewhere in the bottom Riemann sheet. In this case, we have only two Riemann sheets, the proper one and the improper one. That is because we only have one pair of branch points. Now, since the steepest descent path is partly on the top and partly on the on the bottom Riemann sheet, the bottom leg, the dashed line here, may sweep across the pole as if the observation angle is sufficiently large. Okay, and therefore it captures some pole. But since we are on the improper sheet, take in mind that now the imaginary part of a vertical wave number, KZ1, evaluated at the leaky wave pole, is larger than 0. Okay, so the radiation condition is not satisfied. So what are leaky waves? Leaky waves are waves with a complex, generally complex wave number. The real part is the phase constant and is typically indicated with beta, whereas the imaginary part is different from 0 and it's the so-called attenuation or leakage constant, and it's indicated with alpha, or better, minus alpha, imaginary part. Now this imaginary part, and that's important, will be present also if all the media are lossless. So the presence of an attenuation in the wave is not related to the presence, or not only related to losses in the media, if any. Okay. If that imaginary part is not too large, that imaginary part accounts for power leakage via radiation. So that's why we call it leakage constant. Okay, and that's also why we call those modes leaky modes, or also sometimes radiation modes. That is because they radiate while propagating. So this is a kind of wave that loses power, and it loses power in the upper unbound medium. So this is a kind of wave that can only exist in some open waveguide. However, if the imaginary part is too large, then there is also a second mechanism, a second physical mechanism, that is the mechanism of accumulation of reactive energy. So in that case, the occurrence of an imaginary part is closer to say the evanescent character of a mode below cutoff. Okay, so that occurs also in closed waveguides below some frequency, characteristic frequency. The cutoff frequency, you know that modes do not propagate, but they rather store reactive energy without transporting any real power. So something similar, even though not completely equal, occurs for leaky modes when the attenuation constant becomes too large. Generally, there will be a mix of the two effects, the leakage effect and the reactive effect. And the transition between the two is not sharp, but is blurred. Okay. Now let us come back to the complex plane. If you observe the field at some small angle, the steepest descent path will be like the gray path here, the wider one. And in that case, consider that the original path was along the real axis. So if you consider the deformation from the old to the new path, you will see that the pole, the leaky pole that is located here on the bottom Riemann sheet, is not captured. So it does not give you any contribution. Whereas if you increase the observation angle theta beyond some threshold, you will capture the pole, and so you will get a residue contribution. The threshold angle is, of course, defined by the steep descent path that goes all the way through the leaky wave pole. Okay, that's the purple one that is associated with this particular saddle point, K1 times the sine of this threshold angle. Now, since this saddle point, as you can see in the figure, is on the right of the leaky wave pole, and that is because of the shape of the steepest descent path, then K1 sine theta threshold will be strictly larger than beta, which is the real part of the leaky pole. Okay. However, in many typical situations, pole will be quite close to the real axis. So even though if it is complex, and so it lies in the fourth quadrant, it is so close to the real axis that its attenuation constant is a very small quantity, so it's almost negligible, to the point that the saddle point will occur very close to the pole, and therefore K1 sine theta threshold will be approximately, even though not exactly equal to the beta, so to the phase constant of the leaky mode wave number. Now this means that there will be an angular region inside which the leaky pole is captured, and that is the angular region defined by the cone having half aperture given by the threshold angle. The axis of this cone is the z-axis. So on the outside of this cone, in the shaded area here I have indicated the shaded area only in one cut, so in the rho z plane, but you can imagine that this region is rotated along the z-axis. Okay, so inside this shaded area, the leaky wave exists. That is, technically, the relevant leaky wave pole is captured in the deformation of the integration path from the original one to the steepest descent path. If we look at the phase fronts, it's interesting that inside this angular region, if again we stick to the rho z plane, the wavefronts of the leaky wave are those straight lines that are orthogonal to the phase vector beta. However, since the wave has a complex wave number along rho, by separability, it will also have a complex wave number along z. And so therefore, we will have, in addition to a phase vector beta, also an attenuation vector alpha. So the wave is not a homogeneous wave. Okay. And since the upper medium is typically air, so it's lossless, can be considered as lossless, the phase vector and the attenuation vector of this wave will be orthogonal. So here I am describing the situation of the phase and attenuation vectors of a non-homogeneous plane wave. Of course, a leaky wave in a general three-dimensional structure is not a simple plane wave, but it's rather representable as a plane wave spectrum. However, the elementary plane waves that build up this spectrum have this kind of situation for beta and alpha. And note that the direction of beta, this has been exaggerated in this picture, but is not parallel to the edge of the angular region of existence of the leaky wave. That is because, as we saw before, the sign of theta threshold is larger than beta. Okay, so those are incident. But exactly for this reason, you can prove, and that's a useful exercise, that if you project the phase vector beta onto the edge of onto the boundary of the region of existence, what you get is exactly K1, that is the wave number in the upper medium. So this means that there is again phase matching between the conical wavefronts of the leaky wave and the spherical wavefronts of the geometrical optics fields, that is the direct wave, also termed space wave. This is probably something that I should have said in the last lesson. The direct geometrical optic wave, that is the contribution of saddle points, that is the dominant asymptotic contribution to the wave, is sometimes also called space wave. So here we are observing the matching, the phase matching between the space wave or geometrical optics field and the leaky wave wavefronts. Okay. Now, in uniform structures with common materials like ordinary dielectric media, as I mentioned before, leaky poles lie on improper Riemann sheets, and therefore the amplitude of the associated leaky wave increase exponentially at infinity, so they do not satisfy the radiation condition at infinity. Of course, a wave whose amplitude goes to infinity exponentially is something quite strange, that is quite unphysical, because no wave may become large as you wish for physical reasons. So this unphysical feature of the leaky waves was quite puzzling for the first who studied leaky waves, and this occurred in the 40s and 50s. It was soon clear that this was only an apparent puzzle. That is because the leaky wave does not exist everywhere, so it is not existent all the way down to infinity, but it is limited angularly, as we observed before. So if you look inside the angular region, you will actually find that there is an exponential increase of the field if you go far from the interface. However, when you reach the boundary, that is theta threshold, the wave simply abruptly ceases to exist. So the exponential increase stops. And that can be grasped also by sticking again to a ray optics model of the mechanism of radiation that is intrinsic to leaky waves. Consider a leaky wave that is excited somewhere around the z-axis and then therefore propagates radially along the rho axis. Since this wave radiates, its wave number along rho is a complex number with an attenuation constant, and therefore the real power associated with the wave decreases with rho. If you increase rho, there will be an exponential decrease, e2 minus 2 alpha rho, where the 2 comes, of course, from the fact that power is quadratic in the field. And this radiation can be represented in ray optics terms by drawing the rays that are emitted at the upper interface, that is equivalent to an aperture plane using an antenna jargon. And if you look at the rays that are emitted close to the z-axis, those rays are associated with some values of rho, where the power of the wave is still consistent. But if you increase rho, the power decays exponentially, as we said. So the associated rays will lose intensity. Okay, so here the thickness of the rays is proportional to the intensity. Now, if you look at the field by fixing a value of rho, so along some line like the dashed gray line here, and you increase z, what you see is that you will encounter progressively growing quantities of power, that is rays with thicker and thicker rays. And this is exactly the mechanism of exponential increase that is associated with the improper nature of the leaky wave. So there is no puzzle. This is what is actually observed. However, this stops when you reach the upper boundary. So when you get to the threshold angle, okay, beyond which essentially the field is dominated by the space wave. So by the dominant asymptotics due to the saddle point or the geometrical optics field. Note that this improper nature is not extended to all kinds of leaky waves. There also exist proper leaky waves. However, to get those kind of waves, you need to either consider structures with some special medium, like, for example, a metamaterial with negative value of the permittivity and of the permeability, or you need to consider periodic structures. That is, structures that are fundamentally different from the one we are considering here. In that case, periodicity would enforce a structure of the field that is more complicated than the one for fields in uniform structures. It is described by the so-called Flockade Theorem, which involves the existence of many waves called space waves. And in that case, it is possible to have a much more complicated and rich, a richer picture, in which also proper leaky waves may exist. In that case, radiation would occur in a backward direction. So you should consider that those rays would point backward while the wave propagates in the positive rho direction. The power is emitted in the negative z direction. And in that case, you would have a proper behavior that increasing at infinity. Now, what's the use of studying leaky waves? Actually, if you perform a direct asymptotic evaluation of the far field, so the field very far from the source in the upper medium, you will find that the leaky wave field, even inside its region of definition, is anyway exponentially attenuating with rho, or better with r, that is the distance from the origin, the spherical distance from the origin. So it is always asymptotically negligible. It is beyond all orders in rho with respect to the space wave. However, it may still play a crucial role in the study of the far field, because if the leaky wave pole is captured, a at least for some angles, that is, its phase constant beta is less than k1, as in the examples I showed you so far. And this means that the wave is radially fast, as opposed to the slow character of surface waves. And in addition, second, the pole, the leaky wave pole, is close to the real axis, so alpha is much less than beta. This means that the leaky wave is weakly attenuated. And furthermore, if the relevant residue is not negligible, which means that your source couples to the wave, that is, it injects power into that kind of wave, and in other terms, the leaky wave is well excited by the source, then the leaky wave pole may still provide the dominant contribution to the integrand. That is because you have a pole very close to the real axis, and therefore its presence may dominate the shape of the integrand, in particular between the origin of the complex plane and the branch point K1 in the so-called visible range of integration that corresponds to uniform plane waves in the plane wave spectral representation of the field. Now, since the integrand, when you evaluate the integrand at k rho equal to k1 sine theta is by definition up to constants, the far field pattern of the source, this means that the angular dependence of the far field pattern will be essentially dominated by the presence of this leaky wave pole. And this is the principle by which leaky waves are used to shape the radiation pattern in an important class of radiators, of antennas, that are known as leaky wave antennas. Those radiators are based on open electromagnetic waveguides. For example, you can take a rectangular waveguide, you can open its narrow wall progressively in order to let radiation escape from the closed environment. And when the structure is made open, one can see that the relevant modal spectrum also contains leaky poles, which may shape the radiation pattern. And by the way, there are very effective and convenient design procedures in order to synthesize various classes of radiation patterns by progressively modifying the shape of the aperture during the propagation of the leaky wave. So there is a design process associated to leaky wave antennas that makes them very versatile in applications. The one on the left is one classical example of one-dimensional leaky wave antenna, where one-dimensional comes from the fact that the leaky wave propagates essentially in one direction only in space, that is the direction of cylindrical symmetry of the waveguide. But if you have a planar structure, as the one we have considered so far, and you excite it with some three-dimensional source like coaxial cable or an aperture in the ground plane, and so on, then what you get are the cylindrically spreading waves that we discussed in connection with leaky and surface waves. And so you have an example of a two-dimensional leaky wave antenna whose radiation pattern is typically conical, or it can be either also a single beam pointing in the broadside direction. Okay. In this last slide, I illustrate you the concept that I discussed before. Here you can see an extension of the angle theta, of the spherical angle theta, to the complex variable phi. So we are now in the complex plane of the angle phi r plus j phi j, where you can see phi r here on this axis and phi j on this axis. When phi r is equal to pi over 2 and phi j is equal to 0, here we have the branch point K1. And here you can see in this color scale, the black indicates lower values of the absolute value of the modulus of the function, whereas white indicates high values. You can see the presence of poles where the colors go to lighter tones. For example, here you have a leaky wave pole that is very close to the real axis. The real axis is this white line here. And you may also observe a surface wave pole which is, however, far from the real axis. That is because it's associated with a complex angle, the angle being pi over 2 plus j, some imaginary part, okay? As exactly as in the case of the evanescent wave that is produced as a transmitted wave when the incident is beyond the critical angle. So that's the same kind of complex angle. Now, since this pole is far removed from the real axis, that is from the visible range, it does not affect much, or does not affect at all, the shape of the radiation pattern. Whereas the leaky wave, even though it is improper, so it is located on the bottom Riemann sheet, however, it is very close on the Riemann surface to the real axis. So it determines the presence of a huge peak or spike in the integrand. And this spike reflects in the presence of a narrow main beam in the radiation pattern that occurs when the angle theta is such that the beta, the phase constant of the leaky wave, is equal to k1 sine theta. So we have a simple link between the angle of the main beam and the phase constant of the leaky mode. Of course, if you let the leaky pole go closer and closer to the real axis, that is, if you decrease its imaginary part or its attenuation constant, this spike will be more and more important. It will be higher in value and narrower in width. So you will get a more directive pattern. That is, the way to obtain very directive leaky wave antennas is to have a leaky pole with a very small imaginary part. However, you will need, of course, a very large antenna, because if the wave propagates with a small attenuation and you wish to radiate most of its power, this means that you will need to accommodate for a very long aperture so that the wave has lost most of its power when it reaches the end of the waveguide. Okay, so we have discussed what are leaky waves. They are waves associated with pole singularities, and also their application to a class of radiators known as leaky wave antennas. You will find more details about what I have discussed today, not only in the classical book by Felsen and Markowitz, Radiation and Scattering of Waves, but also in a beautiful report by Felsen on lateral waves, which is freely available on the web. So if you Google the name, you will find the PDF easily. And I also give you a very good general reference on leaky waves, surface wave antennas, taken from the book of Collin, edited by Collin and Zucker, Antenna Theory. That's an old but very good book on antennas. It was published in 1969. Every chapter has a different author. In particular, we are interested here in the chapter by Hessel, General Characteristics of Traveling Wave Antennas, which discusses many things related to leaky and surface waves in general. In particular, leaky wave antennas are discussed by Tamir, and Zucker discusses instead surface wave antennas. Those are chapters 19, 20, and 21 in this two-part book. So we are in the second volume of this book. And I think that it's all for today. So I will stop here and thank again you for your attention. I will make you available these slides. I have found some typos in the slides of the previous lesson, so I will replace the PDF that is on the e-learning website, and I also will send to Fabrizio Loreto and Andris Stoia the slides of the last lesson and of today as soon as possible. So see you next week for the last two lessons of the course. Thank you and bye-bye.
Bye bye.
Bye bye. Thank you.
Grazie Paolo, ciao.